and blue. And we have a representation model like the H, and we also have a decision boundary. So this additive noise will cheating this deep representation model to relocate this model to a better area in the established decision boundary. So the problem becomes how to find a minimize distance to let this decision boundary to recognize and as this new target model to a source model, and then you can find out this adaptation can be as a shorter path doing this transformation with this representation power. I'm not sure
Okay, I understand.
Yeah.
Yeah, so you're saying that, so basically what this, just to reiterate, there is a fixed decision boundary which the classifier constructs. So you're trying to map the new target data points to the data points that it was trained on to obtain that decision boundary. So you're essentially trying to map the data points to the other data points that it was trained on. But my question is, isn't this sort of the same as what domain adaptation does? When you have two domains, you try to move the data samples as close as possible to each other in the same space so that the classifier has an easy job of constructing a decision boundary. Isn't it somewhat similar to
Yes,
that?
yes. So I think there is some similarity, but the difference is like the data source they are different, and then the model parameter they have some constraint, the updating constraint. But we can actually use the documentation theory or some mechanism to analysis this phenomenon. Yeah, I agree. Yeah.
And is there any like statistical consequences of mapping the new target points to the old data points that it was used to obtain the decision boundary? Does it affect how does it affect generalization, or how does it affect robustness? I believe you'll have that later in the talk, but I'm just curious.
Yeah, it's a good question. So if you really look at this problem, saying how this additive perturbation will affect the decision boundary for neural network in general. So originally, people look at this perturbation for robustness perspective, but in the reprogramming, right now we don't really have a lot of reprogramming work. But in reprogramming, we trying to use this trainable perturbation for adaptation. So, but doing this adaptation, we are look at this decision boundary again. But right now is how we can include this target data inside this decision boundary. So they can have two. From my understanding, they can have two approach. The first, you can calculate the margin between this decision boundary by margin estimation. So this is how mostly the domain adaptation work. Another way is you can use some local estimation by the real analysis. Mostly is the Lipschitz analysis we talked before, to estimate where where is the decision boundary and how the data will affect the modification of this decision boundary for the final prediction. So, and another way is to use some probability measurement, but they will be kind of similar to the margin estimation. Yeah. Hope this reserve your questions. Yeah.
Yeah, sure. Yeah, all right. We
Yeah,
got it.
it's a good
Thanks.
question, and I believe it's an open question, and they have a lot of low hanging fruit. But just feel free to email me, or if you're looking for future collaboration, I will talk about this in the last slide. Yeah,
Sure.
the end of the slide. Yeah.
All right.
Right. So I'm not sure the audience are coming from the theoretical or more application-based background, but for today, I'll just briefly talk about how we do this analysis. So I don't really want to go into the detail, but instead, we are motivated how we addressing this theoretical analysis. So how we analysis this reprogramming effect is still basing on this domain adaptation. So we use some like terminology from or some samples from domain adaptation. So first we can look at we have a source and target domain. But one thing difference is we have the space in the source and target data samples. For example, the space for this sample can be different, or the input shape or the labels can be different. So which is the X of source and X of target. And also we have the Y of the source labels and target label. And then we have two distribution with the source data set and the target data set. So for each time, we just sample a pair from this source, from this data set for training data or validation the result. And then we have the source label, because we know if we want to fix the model, the source label is the issues. So we have the a K as a notation here. And then for a pre-trained K-way source classification model, the model is actually do this softmax prediction between 1 and 0 on this K. And then we have some constraint of this neural network saying this they are softmax, so the sum of the softmax should be equal to 1. And then we have the pre-softmax logic, so which is the representation after the deep representation power before the softmax. And then finally, there are two things important during this analysis. The first is the risk functions of the X and Y on the classifier F. So you can think of this prediction of a Y can be have a loss. So with a lower loss, so the prediction will be much better. And finally, if we really look over the data set, we will have a population level risk based on this classifier, because we want to add a noise on this X. So we also want to estimate this distribution adaptation during this nonlinear transformation. So we have this population risk analysis. So here this additive input transformation on the target data will parameter by a theta. So you can see this X will add a theta, which is the theta is trainable. But in the neural network, mostly the Z is trainable. Oh, sorry, it's in the fine-tuning based masses, the Z is trainable with the theta. But right now, we parameterize this theta for the noise on this target data. So we have some hypotheses before we're doing this reprogramming. So first, the source risk is epsilon source. So we want to, the source risks are mostly fixed because the model are pre-trained. So here is the loss from the source model. This you can think of is the prediction loss of a pre-trained speech model or a pre-trained image net model, because the model, sometimes the model is not 100%, or most of the times not 100% accurate. So we still have a prediction loss and associated with this source risk. And then the second is the source to the target label space mapping. This is how we do this mapping, and you can do it randomly, or you can do it one by one, or you can do it many by one. So many by one, you can understand is ensemble some prediction from the source model to a target domain. So after this ensemble process, mostly this prediction can be more general, because you take the prediction insight from each as per from a kind of a voting perspective. And second, based on the reprogramming, the target loss with these additive transformation functions can be represented as like here. So here is the xt at the delta. I'm not sure if the notation is big enough. Can you see this notation? Sorry.
Yeah, I'm able to see it.
Yeah, appreciate it. So you can see this x of plus delta and the prediction label. So we actually will still use a y label for prediction, and then we will do some label mapping as the assumption. We will switch the target data to the source data, because you want to mapping back to the pre-trained source model. And then you use by this reprogramming to associate with this source loss, which is the condition B here. And you can reformulate this target loss to source loss by this the third hypothesis. And then the idea become you want to learn a transformation functions for this reprogramming denoted by this delta star here, which is trying to minimize this delta from this source model population source model risk with reprogramming loss objective. And finally, we have domain dependence drawing from the source and target data. So saying we have tails source and T, they like represent for two different distribution. So right now you want to have this probability density function over this data set. So saying you have a sort just recall this data distribution we introduced in the very beginning. So we can use this probability density to estimate the source data and the target data, and let this density function, which means this distribution, become much closer in a high dimensional manifold. So it's the intuition for this hypothesis. So, and then we have the lemma 1. So really the detail about this proof I put in the paper, but here is saying we have this distribution from this mu z and the mu z prime from this the probability measurement from the logistic representation from this Fritz Preacher model with x and the x prime. You can use the Wasserstein distance to measure this decision, this probability density, and then you can see if a reprogramming process going well, this density, this distance will be much closer. And one good news is, if you're familiar with the Wasserstein measurement, so if they are one dimension, so they have closed form solution. So in our case, in one-dimensional data, so this measurement actually have a closed form solution. And then here is the population risk, which will be bounded by this Wasserstein distance. And if you just tired about this mathematics, here is the conclusion about our theory. So saying we have a additive noise transformation during this reprogramming process, this risk will be bounded by the source model risk, which is some error from the source model, and also have plus this representation alignment loss via the reprogramming. So how to interpret this theory? We can find out if the reprogramming model can perform better, which means a lower risk when the source model have a lower source risk and small representation loss, which means the source model have a better prediction power. Meanwhile, this alignment process can be also going well. So in this work, we use psi Wasserstein distance to measure this distribution in the latent space to prove our theories actually work well as a candidate explanation for this reprogramming. Yeah.
I have a quick question. So,
Sure.
okay, I understand that. I understand why this bound works. It's kind of obvious that you have a better source model. It's easier to mitigate the new target samples by adding the additive noise. What I'm concerned is, I'm not sure if I'm incorrect, but this theorem doesn't take into account the. So if you imagine these to be finite sets, like the source data to be a finite set and the target data that you have is a finite set, does this theorem accounts for the distance between the two finite sets at all?
Can you clarify why is the finite state in your definition?
So is this the imagine the data to lie in some metric space,
Right.
and you have the source data to be just a finite set, and you get this new target data that you want to map to the source data to fit the original decision boundary. So is there any uh, like any change you would require if the distance between the two sets are large or small?
Yeah, I think as you say, right now we didn't consider the knowledge inside these two distribution, right? So for example, the knowledge in the speech, maybe the open or on, this kind of things share the same phonomy, they will be much closer. As you say, they can be alongside with a finite state, finite like training like domain or subdomains as an example, and also for target domain also have some fine like subdomain. But as you said, maybe from the documentation perspective, you can also include in this subdomain for classification, or you can also optimize this subdomain distance. But in this area, we don't really require this subdomain estimation. But in our recent work, we also consider this subdomain, and when we do this mapping, for example, you do the clustering and incorporate some domain knowledge from the source model, and then you do this prediction. So I think this potential future work combine this estimation. Yeah.
Great, interesting. Thanks.
Yeah. Hope I answer your questions. Yeah.
Yeah.
Yeah. It's a good question. Yeah. Any other questions? Right. So just the takeaway is like we can estimate this kind of alignment loss by statistical measurement to justify how a reprogramming working well from one adaptation to other adaptation. So let's really
Also,
yeah, please.
so one last question. What was K there? I might have missed that. What is the K-way source neural network?
Yes, the K-way means, for example, ImageNet pre-train have a thousand class, right? So the
Yeah.
K equal to 1,000 in this definition. Is
Oh,
the
okay. Okay.
yeah.
Okay. Got it.
Yeah. So you can find out if the pre-train model they actually have much class, this bound will be much loose. But if the pre-train model they only have a really few prediction, this bound will be much tight. Yeah, which is clear. Yeah.
Right. So
Yeah,
it's sort of like a superset subset kind of. So if the source model was trained on a superset kind of data set, then if you're moving the data points of a target domain, which is sort of a subset of that superset, then it is much easier to do that, right?
Yes, yes, yes. And I believe these methods apply on-site statistical-based model, for example, SVN or Bayesian modeling. Uh, these K-ways like advantage but will be much obvious. But for neural network, I think mostly this bound will affect by the source risk. Yeah.
Right. Thank you. Bharat, I guess you had a question.
yeah. So I had a question related to this delta perturbation that we are learning. So it's similar to like what we do in adversarial training. Just like in adversarial training, we have a min-max optimization problem where we maximize over those delta parameters to say that okay, which perturbations will basically make my loss to be higher. But here we are saying that okay, we want to find the perturbation delta, which makes our loss smaller on that. So basically the examples or the labels for which the addition boundary not correctly classified get it correct. Basically, that's what it's saying. Like if I want to just wrap it around as a
Yeah,
loss
I
function.
think it's one kind of interpretation, but well, I just want to add one thing different with adversary is the adversary robustness mainly consider the source model risk, but right now we have to also consider this alignment from this adaptation. Yeah, so I think it's the
Yeah,
difference, but I believe some kind of the adversary robustness mathematical approach can apply on this new reprogramming field. Yeah.
yeah, okay. Thanks.
Yeah, it's a good question. And I think one challenging thing is like I just want to highlight the first paper on this reprogramming find out in the iClear 2018, but there's only one work or two work after this 3 years process, and people don't understand how these things work. So I think by applying this approach or combining some analysis from both domain adaptation and adversarial robustness, we can understand this phenomenon well. And these methods only rely on really few training like parameters, so they can have more application for example on device or other applications. Yeah.
Yeah.
Right. So, but before that, I was also want to highlight some challenge on this work. So some engineering challenge. So, for example, reprogramming a waveform or wave signal to time series look like simple and straightforward, but why people didn't do it before? One thing is for speech processing or acoustic modeling, people mostly will use the feature, the digital filter to pick out the feature, right? For example, the input is signal. Usually they have a signal processing and take out the acoustic feature, and then use this acoustic feature for training. So that make some challenge for this reprogramming process because we require the model training end to end. That means this DSP process should be also including the model for the gradient propagation. So when I work on this project, it's around 1.5 years ago. We find out these issues because mostly this acoustic feature extractor, they are not differentiable. So at that time, we find a specific audio layer that can unlike extracting the features, and then you can just directly feed this signal for these layers and train the model end to end. So that means you can directly use the reprogramming layer, add a trainable noise on the input, and then the audio layer, although it's not trainable, but it's differentiable, and the other side is the precision model. And finally, we do this label mapping. But right now, as you know, I think in recent half years, both TensorFlow and PyTorch, they support DSP differentiable layer. So right now, I think this application can be much wider. Yeah. But as you say, you can see here is the additive noise process, and here is the differentiable layer, and the other way are freeze because we need this distribution boundary. And finally, the label mapping. So this model was based on a transformer-based attention model, which is pick out the RN by querying and do this sales of attention here. Another thing is we also apply a stronger model by UNet. So this blue block are also pre-trained. But we find out sometimes if the model architecture are similar, a better source arrow will not really means a better reprogramming. So we do some ablation and find out this attention only pre-trained model works better. Yeah. And you can find out the source code here, which is open source and open for collaboration. Yeah, so here is the performance on the time series dataset called the UCR archive. So you can find out the first column is about the dataset. The coffee means the spectral information from the coffee. ECG means the ECG signal pick up from the sensor. Earthquake fault is kind of the sensor's data for anomaly detection or classification. So here we provide the type information, and here is the input size. Input size is important because for the acoustic data we have around 60,000 sampling points. But if we merging this input in this sampling point, we associate an input augmentation process, which I'll talk later. But we find out the input size can be also important during this reprogramming by augment this input size. And the training data is size is kind of diverse, but which is interesting. For example, it's hard to think you can train a model with a really deep model like the attention model with RNN and convolution layer with 28 data. Same thing happened for this the data like the Sony sensor data or the other data. So which indicate if we reprogramming a precision model well, we can empower previously those lower resource data set which can hard to reconstruct a deep model, but we can borrow the exceeding representation power from the deep model with this trainable noise. So the SOTA. Please.
Yeah, I have a very stupid question. So what happens when the source domains in like the source data that you trained on originally has a smaller input size than the target data. Just like you gave the example in the ImageNet MNIST one, where MNIST is much smaller than ImageNet, so you put it in the center and you have a big space around it to put the additive noise. But what if you had done it in reverse, MNIST to ImageNet, where ImageNet is much larger than MNIST?
So right now, I think it's open questions. So right now, when we do this work, we constrain the input size should be smaller than the source domain. But recently, we are thinking of you can clip this input like a query, and you can just, for example, you can cut this signal into pieces, and then you still running this reprogramming, but you concat this prediction again. You just like use reprogramming as a filter to go over part of the signal. So this a potential approach. Yeah.
Oh, so it is more like a MLP or transformer approach where you break it down to like individual patches or individual tokens and do reprogramming on individual patches rather than the full input.
Yeah, it's one of idea recently we are trying. So if you have any suggestion, we are also welcome. Yeah, but I think it's a really good question and it's open. Yeah, open questions. Yeah.
All right, thanks.
Thanks again. And for the SOTA, which means we conclude a lot of time series processing methods include more digital signal processing methods like the wavelet based methods and also the dynamic time warping and also deep neural network based methods. If you are interested on the detail, you can look at the section 5.3 in the paper. But I would say the comparison is not fair to us because some of the approach, they actually ensemble a lot of different models for the prediction. And then one thing associated with the size issue I want to highlight, the class issues are also limits. For example, if the target domain class is larger than the pre-trained model, because right now we don't really have a good way to do it. For example, if the pre-trained model for Google speech command have 36 classes, but the target data say should be smaller to this 66. But larger than 66, right now we don't really have a solution for it. Yeah.
So the other question here is, there is a strong assumption that you have a labeled target data set, right?
Right now, because in this work we don't have this kind of assumption, but you can do it in the unsupervised way, I believe. But in this work we have assumption on we have this label data. Yeah, but they don't have conflict if you have unlabeled data and you want to do some meta learning process. Yeah.
And what I'm also concerned is, in a practical, realistic approach, if we are to do this, how does this? Is there any way that this can mitigate, for example, noisy labels in the target data?
If I understand correctly, the noisy label means the data they have. You mean that the data actually the domain is actually much sparse, right? For
Yeah.
example,
So
yeah.
what I'm saying is, if what I'm saying is the mapping that you're doing for the target data sample to the source data sample, can that in any way mitigate the label corruption that might be associated to the target data sample?
Yeah, right now I didn't we didn't do this analysis on the robustness of this reprogramming. So I think that belong to the alignment loss. But right now we didn't do this kind of analysis. But you can think that if you trying to attack a noisy speech samples in the virtual attack perspective, this both the clean and the noisy speech they can still attack because this additive noise is trying to use the transformation in a high dimension metaphor. So in the original distribution, maybe they are sparse, but in high dimension space, they can still be near. Yeah.
Right. Okay. Got it.
Yeah.
Thanks.
Yeah, it's a good question. But you can find out, we compare with the state of the art and V2SS-A, which is with the attention-based methods, and V2SU, which means with a larger parameter but with the UNet, and transfer learning with the architecture A. This V2SA is actually a good potential methods for this kind of data. So it actually shows competitive result in diverse title data. So which is an excited result. And finally, we want to see our statistical approach is correct or not. So we use this training time reprogramming analysis with the V2S and the data set to analysis if the distance actually become closer. So from our analysis, here we demonstrate one of the data set. So the x axis is the apples, and the y axis is the validation accuracy, the test accuracy. You can find out when the test accuracy are increased, this loss are decreased, and this side Watson's distance also decrease. One thing I want to highlight is not monotony is decreasing. So sometimes these side Watson's distance are still increased, but the loss are decreased. So they have some correlation, but they are not monotonic correlated. Yeah. So we also.
I have a question. What?
Yeah, please.
So this sliced, what does this mean by sliced? Sliced WSG?
You mean the color or?
Yeah, no. The sliced resistant distance, right? So what does this sliced mean? Like what?
Yeah, so for Watson distance, you compute the distance between two distribution, right? But you have to make a hypothesis on this distribution. So side Watson distance is one of the classic measurement. So they are mapping to this distribution to a hypothesis. For example, Gaussian. So this process called the side, and then you do this Watson distance measurement. Yeah.
Oh, okay. Great, thanks.
Yeah. It's a good question.
I have one more question. So at the start of the talk, you said that this is a much easier thing to do because you're just optimizing one parameter which generates the additive noise rather than fine-tuning the whole model or fine-tuning the final layer. So is that sort of universally true? Did you see it in your experiments that convergence using additive noise is much faster than fine-tuning the model explicitly on the target data?
Oh, it's a good question. I think I don't want to make an overclaim, but for some time series data, if the data is around 100, so the convergence speech will be faster than training from scratch or in fine-tuning. But the data is sparse, they still have some instability when you use this reprogramming. Yeah. Another open question is like in this paper, we claim this reprogramming work well in this time series only rely on this additive noise. But in really recent work, we also find out you can both do this reprogramming and fine-tuning. So I think we'll release a paper in early October. So we also test different ablation study for reprogramming with this fine-tuning. Yeah, but I think as we discussed, it's open questions mostly. Yeah.
Great, interesting. Thanks.
Yeah. So yeah, thank you for the questions, guys. And then let's look at some visualization after we have this result and somehow just we support with our theoretical finding. So here I give a visualization on this signal, which is the target time series signal. For example, here is the ECG, for example. You can see the sequence sampling point is not a lot. And the blue data is actually the reprogrammed noise. So we try different input argumentation, and we find this argumentation slightly improved the model performance, but it's not critical. But another thing people just mentioned is like if the prediction model, even the prediction model are freeze, they are look at its target signal or they are look at this reprogrammed noise. So we are look at analysis this model from two perspectives. Since we use attention-based methods, although the attention doesn't means explanation, but it showing some correlations, right? So if we look at this sequence labels attention, this attention actually look at this target data. Here's the attention hat. But if you look at this spectrum level, and you look at this spectrum by, here is the spectrum from the sense signal we're doing. So here you can see there's the energy intensity on the target signal, and the other side is the power spectrum about this reprogram noise. So the first convolution layer, they actually look at this target signal, which is the here. And this yellow color means higher heat and higher attention during these cuts, deviation mapping by global average pooling. But the second convolution layer, interestingly, they both look at the manifold about this target signal, which means the shape about this target power spectrum. But mostly they look at the noise for them to doing this adaptation. So I have to say the model both rely on the target signal and the additive noise for making the final prediction, even the model is not tuning and the parameter are freeze. Yeah. Which is interesting. Yeah. And finally, we do some testing analysis to probe this logic presentation on these two different data sets. The first one is strawberry spectrum. You can see here is before reprogramming, and which is not is randomly initiated. And here is fine-tuned transfer learning. So in this data set, the prediction is not have a lot of the accuracy don't have a lot of difference, but you can see this manifold here and here that difference. And also for ECG 5000, both of the model predictions are around 90%, but you can see the manifold in reprogramming is actually quite interesting. If you calculate the center between this group, this distance will be larger than this one, which is interesting finding. And as the discussion, we find out this reprogramming work well. And firstly, I think we provide the first theoretical justification on this reprogramming. And currently, we're working for speech-to-speech processing with the reprogramming and some sequence modeling tasks, including time series and language modeling. And some of the recent work I briefly mentioned. So it's like, for example, different mapping technique or combined with fine tuning, they also work. And if you're interested to collaborate, feel free to email me and ping you if you have a specific task or you want to just work on some tasks we are already working on. And I also want to thank my collaborator on this work, Yun from Columbia and Data Ping Chen from IBM Research. And here is some acknowledgement and reference. So by doing this work, I rely on some of my experience working on acoustic classification, which we can find out the code here and here, which is the state-of-the-art model for acoustic sense classification. And also we look at some pre-trained methods in the time series, and then some reprogramming reference. Yeah.
Oh.
Any questions? Thanks.
Like I can think of another application, like you have said that like this can be directly applied to NLP. So like we can think of NLP as a sequence of tokens directly. So we can have a discrete tokens, and then we can have those embeddings, like let's say n embeddings, and we can take that n embedding for an image classification model, right? Like we can take that n embeddings and take that as a patches of the image and can pass it to directly image classification model. So I think that can be directly applied.
Yes. I think that will accelerate the universe of the pre-trained models applications. And as far I know, I think some fair team are doing this course model, like fine-tuning and pre-training application. But I think for now, they didn't really work on the reprogramming. Yeah. And we also have a work for coast domain adaptation. So if you are interested, just feel free to email me if you want to discuss your personal questions or if you want to collaborate. Yeah, I think it's it's a blue sea. Yeah, you don't really have to try a lot of architecture again, but you can more look at this adaptation. Yeah.
Okay, thanks.
Thanks.
I have one other potential idea that I can think of is this can be directly applied to online learning or continual learning settings, right? Where you're getting new sets of data over in n tasks and or in batches of time. So you can have a classifier which constructs a decision boundary from the first task, and that same thing can be used for all subsequent tasks that it encounters or all subsequent batches of data that it encounters, right?
Yes. I think one thing different with the pre-trained model plus downstream, which is the population approach, is here you can actually change the domain and somehow change the task. So which is promising. Consider this foundation model or large scale pre-trained model. Yeah.
Oh, right. I think Ajay would have a comment on probably saying this would be ideally the definition of a foundation model. Ajay, do you think that is the case?
Yes. I think there can be a case, but actually, when I work on these masses, I didn't. I'm coming from the adversarial robustness perspective. So, but after I work on this, I kind of believe maybe they can combine with foundational model pretty well. Yeah. So if you have any idea with the foundation model, I think they should be popular, and this committee is not really crowded yet. Yeah.
I had a question like, is there any study about the adversarial robustness of models by reprogramming? Like, uh, an ambition study showing that, okay, when we add some training data noise, and let's say this delta is also added, using some attack procedure using meta learning or any other method, reinforcement learning method. If you add those kind of data, your model will be robust to this because it is reprogrammed in the way that those data perturbation it is used in the training, not just training, but yeah, you can think of this as a training in sense of the parameters and other change. So those trainable parameters in the reprogramming there.
Yes,
So
yes. I think for the theory about the versatile robustness, they can coming from two perspectives. The most popular one is on the network verification. So if you are familiar with this field, they have a way called CROWN, CROWN. Another thing called Clever score, which is rely on the local Lipschitz estimation on the output of the network to estimate if you have additive prediction, how this additive noise on the input, how the output will change. So I think these two kind of analysis may combine with the versatile reprogramming to give another approach on these micro levels like distribution boundaries of those observation. Because right now we look at the distribution, right? So it's kind of the macro level. Yeah.
okay.
Um, yeah, this is very interesting. What according to you, okay, the question I had, which I stated at the earlier part of the talk as well, is that I think introducing some sort of distance metric into that inequality bound would give a more stricter or more tighter constraint on how to do reprogramming, because right now the assumption is that the data lies on some manifold, and you do not technically account whether the target data is like 1 unit away or 100 units away, right? You're just accounting whether you are able to map it based on the loss of the model on the source data, and the representation loss that you introduce into that inequality, right? So I'm
Yes.
just concerned whether distance plays a role, how far apart two data sets are, because I think that might be important in considering in understanding how fast it converges. So, for example, if the distance is very, very large, then it might take significantly more time to converge, and thus you can then have sort of a threshold, right? You can say if the distance is more than this threshold, then you should do fine tuning rather than reprogramming. But if the distance is below that threshold, then you should do reprogramming. I don't know if I was able to make sense in what I said right now, but
Yeah. I kind of understand your idea is like is based on the scalability of the data and how you associate with the decision boundary. Yes, I think it's a really good point, but right now we didn't really look at it from that direction. So if you are interested, just feel free to send out the email. Yeah.
sure. Ajay, do you have
I
any?
had
Okay, Bharat,
I
yeah.
had like a counter question for that, like what Diganta has just said about the distance between the two data distributions that he was talking about. Isn't like the Western distance tell us about something about the distance between them? Like we have two data distribution, we have some probability they are following some probability distribution P, and we taken mean mu1 and mu2, and we're calculating a Western distance between those two. This tells us about the distance between the data, right? So what
Yes,
exactly you
yes,
were
yes.
talking about?
From the teacher-student learning, if you are familiar with,
Yeah, yeah.
yeah, so there are also some way to minimize this KL divergence, or especially to do this probability measurement between this uh, distribution and further incorporate this distribution matrix as a loss. So I believe both with this divergent matrix, either with the KL divergent or Jason Shannon's divergent, they can help on the conversion if we train with a really large and good representation data. But one thing I didn't mention is like right now it works well on this low resource data, but for exceeding large scale or close domain data, it's a little bit hard to justify the advantage. So maybe you can incorporate this, more established distant measurement methods. Yeah.
The reason I asked because I thought that Wasserstein distance primarily says the distance between the center of the data manifold, right? Am I correct in that? Like, I'm not sure if I am correct in saying that Wasserstein distance
Uh,
doesn't say
I,
the extreme
I
distance.
think since when we do the measurement, we'll do this a distribution mapping process, which means we'll use a statistical hypothesis to mapping this original data. So, for example, Gaussian or some kind of that. So I think this instability of this distribution can still affect, but based on this layer definition, these things are actually have is a closed form, so they can be robust. But how you accurate is another problem. Yeah.
Okay, got it. Um, Ajay, do you have anything?
One one small thing I wanted to ask is like when we start with the signal X, then we have some perturbation data, we get an X dash. So the signal length varies, right? When we add the noise. So is it correct, right? Like the signal length basically changes when we added a noise. It may happen because I saw in your picture that you had then X signal, then after adding a noise, your X signal gets expanded in the time domain, right?
Yes. I think in the original reprogramming paper, there are much engineering approach, so they have some constraint about this range of this adversarial noise. For example, they should belong to a RGB format, something like that. But in our work, we didn't actually constrain this range, so it's what it happens, it happens. Yeah.
Okay, so yeah, okay. So can we think of this as kind of an augmentation to the signal? Like we are basically augmenting it, right? Like in the time domain, we are taking a signal and augmenting it.
Yeah, but I think in the augmentation, we couldn't control where you want to augment. So it's
Yeah, of course.
basically yeah, you just including this the training distribution. But here we actually control the way we want to argument it, and we may make it for this our source data.
Oh, okay. So here your data is initialized uniformly initially, I think, right? Like you
Yeah,
initialize some uniform distribution. Okay, got it. Yeah, thanks.
Yeah, this is more like targeted adversarial attack, but instead of this being adversarial attack, it is just for minimizing the loss.
Loss. Yeah,
yes,
got it.
yes, yes.
Um, okay, great. I don't know if anyone else has any other
Yeah, I
questions.
just want to add. So if you are, if you have friends like interested on this work, just feel free to let me know. And I also, the difference with this research recently, I'm a special area chair in the content speech and language processing. We actually have a special paper called uh, at the end of this October 6th in ICASP. So if you are interested to submit paper, and also feel free to let me know. Yeah.
Sounds good. Yeah, great. This is very interesting. I'll, I have few ideas, but I'll first read the paper and try to understand everything in all the details, and probably I'll reach out after that on email. But thanks
Sure.
for taking the time out today to present this talk. I believe this was as interesting for others as it was for me, and I'm quite optimistic that the community will catch up on reprogramming. Seems like an interesting concept,
Yeah.
and I hope to have you here for your future works to discuss with more members. Uh, this was on a very short notice, which is probably why everyone couldn't join. But we will try to accommodate everyone for the next time when we have you. And also, Ajay can send you the link to the live stream after this on email if you'd like to use that as a reference. I'm not sure if it is a full length because we had some issues at the start,
Sure,
but
sure, sure.
either ways, it was just a test streams for us to validate that everything is working correctly. So, um, yeah, that is it from my end, and thanks again for taking the time out. I hope to talk to you soon again.
Yeah, have a nice weekend, and just let me know if the stream or the video file is ready. Yeah, appreciate it.
Thanks, sir. It
Yeah,
was nice.
nice talk
Thanks.
with you guys. Thanks.
All right. Bye bye.
Have a
Bye.
nice weekend.
You too.